Welcome back to Mechanical Engineering Made Simple.
It's great to be back.
Today we are on a bit of a mission. I've got this stack of engineering texts in front of me, and honestly, they look pretty intimidating.
They usually do.
They all deal with the absolute nightmare scenario for anyone who builds things: failure. But, and this is the catch that really hooked me, we're not just talking about things snapping in half because they weren't strong enough.
Right. If you're only looking at raw material strength, you are missing, well, at least half the picture. We're looking at something much more subtle today.
Exactly. We're moving beyond simple strength. Can this metal hold this weight? And
Yeah.
we're digging into behavior, shape, stability, geometry. So we've gone through these sources and pulled out 3 specific areas that I think are crucial. We're going to cover the basics of tension and compression, then the weird instability of buckling, and finally, the surprisingly complex way circular plates bend.
And that distinction you made is so important. I mean, you can pick the strongest metal alloy in the world, something that can withstand immense force on paper.
Right.
And your structure can still fail catastrophically if you don't understand stability. It's the difference between a material breaking versus a structure becoming unstable and just giving up.
That is a terrifying thought. The idea that the material is fine, but the structure failed. So let's unpack this. We'll start with the basics, something that seems simple on the surface. The steel wire.
The classic tensile test. It's really where it all begins. And the interesting part is what happens when you start adding weight, little by little. At first, for small loads, the wire acts just like a very stiff spring.
And this is where Robert Hooke comes in, from way back in 1678.
Hooke's law, exactly. In this initial stage, the extension is directly proportional to the load. You double the weight, the wire stretches twice as much. It's what we call the linear elastic region.
The key word there being elastic, right?
Precisely.
Meaning if I take the weight off, it snaps right back to its original length. No permanent damage.
Correct. And think about the physics there for a moment. The energy you put into stretching that wire isn't lost. It's stored as strain energy.
Like charging a tiny battery.
Perfect analogy. The atoms inside the metal are just stretching their bonds, but they haven't slipped past each other. They want to go back home.
But the text mentions a boundary, a point of no return, the limit of proportionality.
That's the tipping point, the edge of the cliff. If you keep adding weight, you cross that limit. Your stress strain graph stops being a straight line. You've entered the plastic region.
And plastic means it's permanent.
Yes. Now, when the wire stretches, you're actually doing work to change the internal crystal structure of the metal. Layers of atoms are literally sliding over each other.
So that energy isn't stored anymore.
No, it's gone. That's the big difference. It gets released mostly as heat because those crystals are grinding past each other. If you take the load off now, the wire stays longer. It's permanently deformed.
That makes so much sense. It's why if you bend a paper clip back and forth really fast, it gets warm.
Exactly. That's plastic deformation releasing energy.
Now, the text makes a big deal about the math here. It says we shouldn't just look at the total load, the p-value. We need to look at stress. Why is that distinction so important?
Well, because load by itself is vague. If I tell you I'm putting 1,000 pounds of force on something, is that a lot?
I guess it depends on what the something is.
Right. 1,000 pounds on a thick steel column is nothing. 1,000 pounds on a sewing needle, it's gone. Stress is the intensity of that force. It lets us compare apples to apples no matter the size.
So it's the load, P divided by the cross-sectional area, A.
That's it. Tensile stress equals P over A. That becomes the universal language for how much punishment a material is taking.
The sources then use this to break down materials into 2 camps.
Yeah.
Brittle versus ductile.
Yes, and this really dictates how a structure feels when it fails. Ductile materials like mild steel or copper are, well, they're forgiving. They stretch a lot before they break. They give you a warning.
You can see it sagging or deforming.
Exactly. A brittle material like cast iron or, say, concrete shows very little elongation. Fails suddenly, sometimes explosively, with almost no warning.
Speaking of concrete, there was a chart in the notes that I found pretty surprising. I'm calling it the concrete paradox.
Ha, I like that. It's the defining characteristic of our modern built world. Concrete's strength in compression, when you're squashing it, is massive. You can hold up skyscrapers. But its strength in tension,
When you pull on it.
it's pathetic. It's really, really weak.
How big is the difference we're talking about?
It's about a 10-to-1 ratio. Its tensile strength is only about 10% of its compressive strength.
1/10. That's a huge gap.
It's why you never see concrete used by itself in situations where it's being pulled.
Yeah.
It's always reinforced with steel rebar. The steel handles the tension, and the concrete handles the compression.
Okay, one last cool example from this section before we move on. The rotating rod.
Ah, yes. A great complex loading scenario. Imagine a propeller blade. The force isn't from a weight hanging off it.
It's its own mass trying to fly outward. Centrifugal force.
Right. And the math shows something that's a bit counterintuitive. Where do you think the stress is the highest?
Well, my gut says at the tip, right, where it's moving the fastest.
That's what most people think.
Yeah.
But what's pulling on the very tip?
Yeah, nothing, I guess.
Exactly. The stress at the tip is zero. The material at the center, though, near the hub.
Ah, it has to hold on to the entire rest of the rod.
Correct. So the stress is actually greatest at the axis of rotation, and it drops off to zero at the tip.
So if it fails at the hub.
Precisely. It's a great example of how movement itself creates load.
Okay, so that's tension. We have a good handle on that. Now let's pivot to where it gets, honestly, a bit scary. What happens when you push on things?
This is where we leave the world of simple material strength and enter the world of stability.
Buckling.
Buckling. The text defines it as a condition where a member develops large distortions before the material actually crushes. It just becomes unstable.
This is that nightmare scenario. The material is strong enough, but the shape fails. The classic example is the pin-ended strut.
Right. Imagine a slender column pinned at both ends so it can pivot. If it's short and fat, like a hockey puck, it just squashes.
Pure compression.
But if it's slender, like a yardstick, something else happens. You increase the load, everything seems fine, and then boom, at a certain critical load, it suddenly bows out sideways.
There's a famous formula for this, the Euler formula.
Yes, the Euler load from Leonhard Euler. It's one of the most important equations in structural engineering, hands down.
Let's break it down because the variables tell the whole story.
They really do. The critical load, let's call it PE, depends on the material's stiffness, EI. But the killer variable is in the denominator. It's divided by the length squared.
Length squared, I want to pause on that because the implications are huge.
Massive. Because it's squared, a small change in length has a drastic effect on strength. If you take a column and you make it twice as long, you don't cut its strength in half.
You cut it to a quarter of what it was.
Exactly. 4 times weaker, just by doubling the height. And it's why you see cross-bracing everywhere on bridges and scaffolding. They're cutting that unsupported length in half, which makes it 4 times stronger against buckling.
And the text says the shape it makes is a sine wave.
Yep, it bows out in that classic sine wave shape. Mathematically beautiful, but structurally a total disaster.
But here's where the source material gets real. The Euler formula assumes everything is perfect. A perfectly straight column loaded right in the center. Does that even exist?
The answer is a hard no. In the real world, nothing is perfectly straight. The load is never perfectly centered.
So Euler's formula is just a theoretical ideal.
It's the absolute ceiling of performance. For real engineering, we use something called the Rankine-Gordon formula. It's semi-empirical.
Meaning part theory, part experiment.
Exactly. It creates a bridge. It accounts for the material's crushing strength and its slenderness. If a column is short, it predicts it'll crush. If it's long, it predicts it'll buckle, like Euler says. But for everything in that messy middle ground, it gives you a safe value that accounts for imperfection.
So it's the real-world formula.
You could say that, yeah. It acknowledges that real columns always fail before they reach that perfect Euler load.
Now, there's another type of buckling mentioned that I had never considered. Torsional buckling. It was in the section on a cruciform strut.
A column with a cross-shaped cross-section, like a plus sign.
Right. And it doesn't just bend like a banana, it does something else.
It can twist.
Yeah.
Because of that shape, the whole column might twist around its own vertical axis before it ever bends sideways.
It corkscrews.
In a way, yeah. The text actually shows a graphical boundary. If your dimensions put you above the line, it buckles by bending flexure. But if you're below the line, it buckles by twisting torsion.
A great reminder that geometry is destiny when it comes to failure.
Absolutely. Confusing those modes is how big things fall down.
Okay, let's move to our third and final source. We're leaving sticks and wires and moving to flat surfaces. Circular plates.
Think of a drum head or the top of a piston.
And the text immediately splits this into 2 categories. Small deflection and large deflection. What's the cutoff?
The rule of thumb is the plate's thickness. If the deflection, how much it sags, is less than about half the plate's thickness, We call that a small deflection.
So if I have a 1-inch thick steel plate and it only bows down 1/4 of an inch,
You're in small deflection theory. And in that zone, the plate resists the load primarily through bending or flexure.
Yeah.
It's linear behavior. Push twice as hard, it bends twice as much.
simple enough. But what if I really overload it? What if it deflects more than half its thickness?
Now you're in large deflection theory. And this is where the physics completely shifts. As the plate deflects more, it has to start stretching. It acts less like a stiff board and more like a rubber sheet.
This is the membrane effect.
Exactly. And this leads to a very, very surprising result.
Which is what? Usually, if you push something past its limit, it gets weaker.
Here, the plate's stiffness actually increases.
Wait, what? How does bending something more make it stiffer?
Think about a trampoline. When you stand in the middle, the fabric is pulling inward from all sides, right? When the deflection is large, the plate has to stretch to make that bowl shape. That stretching creates tension across the plate membrane stresses.
And that tension helps support the load.
It helps a lot. You're recruiting a whole new way to resist the force. The source has a graph comparing the two theories.
I'm looking at it now. The linear theory is a straight line, but the large deflection curve bends upward, showing it gets tougher.
The text notes that when the deflection equals the thickness of the plate, that membrane effect is carrying about 65% of the load.
Wow, 65%. So if you ignored it and just used the simple math,
You would be way off. You'd think the plate was much weaker than it actually is. The simple theory just stops working.
it's amazing. We went from a simple wire that behaves linearly to a column that's treacherous and unstable to a plate that actually gets stronger as it deforms.
It really is. And it shows that these equations, Euler's formula, the plate equations, they aren't just academic exercises.
Yeah.
They're the language we use to predict these invisible limits, like buckling, so they never happen in real life.
It completely changes how you look at a bridge or a building. You don't just see strong or weak anymore. You see shapes designed for stability.
And if there's one final takeaway from all this, it's about the role of imperfection.
I was just thinking about that, the Rankin-Gordon formula.
Yes, the perfect theoretical column has one failure load, but a real, slightly imperfect column behaves differently. It needs a different formula.
It's almost a philosophical point to end on. We design for perfection, but true stability only comes when you account for the fact that nothing is ever really perfect.
Well said. Maybe in engineering, as in life, accounting for imperfection is the only way to be truly stable.
That seems like a good place to wrap up this deep dive.
I agree.
If you haven't already, get over to our YouTube channel, Mechanical Engineering Made Simple, where we post hands-on how-to videos, visual breakdowns, and practical engineering walkthroughs you can actually use. A family that solves together stays together.